guys, in this video we are going to see the next two algorithms, the next two software solutions which are used to provide synchronization among the processes. In the last OS class we have learned the lock variable technique and the strict alternation. The drawback of the lock variable was it was unable to guarantee mutual exclusion and bounded waiting. So we implemented that with the strict alternation, but it's still unable to guarantee progress when there is an uninterested process. It preventing the interested process from going into the critical section. So to solve this problem, we came up with an idea of maintaining an array flag which maintains the status of each process whether it is interested or not. Now, the core idea of this algorithm is to consider two processes P1 and P2, and if the process Pi, let's say this as Pi, which you can also say P1. So if the process P1 is interested, then the flag value of that process is set to 1. And if the process P2 is interested to enter into the critical section, then its flag is also set to 1. Now, here we'll consider the process whose turn value is set to 1. Like we'll execute that process which has like the based on the current value of the turn. If the turn value is 1, then we'll execute the process 1, and if the turn value is 2, then we'll execute the next process. And if there is a process waiting condition will occur when a process is when the other process is interested but and the turn is set to that process, then the current process will be in waiting state until the other process completes its execution. It won't get out of the waiting zone. So the core idea is if a process has interested to enter into the critical section and the turn is assigned to that process, then the current process will make itself as uninterested and waits until the turn reaches to the current process, and then it'll make itself interested and executes its critical section. Let us write the implementation of the Dakker's algorithm like in this. In this algorithm, first, if the process is ready to enter into the critical section, it will make the flag of ith process. That process will be true. And it will check the condition that if a flag of the process j is true, which implies that the another process is interested in entering into the critical section, and then it will check the other condition that if the turn is also assigned to that process J, then it will make the current process flag of the process I to false, making itself uninterested and waiting until the turn will arrive to its process ID. Like while turn is equal to J, it will wait, and the moment the turn comes to the process, it will make itself true, and exit its while loop, and here it will perform its critical section and again make the current process to uninterested, and turn changes the turn to the other process. So in this way, the process will be executed independently without interfering in the critical sections. So here, when the other process is interested and the turn is assigned to that value, the current process will change its flag to false and wait until its turn arrives. And when the turn changes to I, it will make itself interested and performs its critical section and make it as uninterested and changes the turn to the next process. So in this way, the Tagore algorithm guarantees all the all the three conditions. Mutual exclusion is guaranteed because the moment the turn value changes to J, the process J can only enter into the critical section after the process I. Progress. Let's check for the progress. Let's suppose there is no process J interested in critical section, then the execution will it will does not enter into the while loop, and it will directly skip this while loop and come to this and starts executing its critical section. So here the uninterested process is not interfering in the interested process in executing its critical section. So progress is also guaranteed. Let's check for bounded waiting. Let's suppose a process I has just completed its critical section, and again when it tries to enter into the critical section, and if there is an interested process, then it will enter into this while loop, but it unable to satisfy this condition, which makes it to stuck in this while loop until the process 2 completes its critical section, which implies that bounded waiting is also guaranteed. So in this way, we have successfully able to implement a solution for synchronization problem. Therefore, Dekker's algorithm is a complete solution. It is a complete solution. But still, the scientists have optimized this solution a little bit, which is also known as Peterson's solution. Here, if we consider this block of code, if we take this and we can see that the current process interest has been changed to false, and the moment it turns arrives, it again changes to true, which is actually useless. We can still obtain the same future by removing this turn, which reduces the lines of code. Now, if we again observe this code can be equivalent to return equivalent to this code flag of j equal to true and turn equal to j. The above code can be simply replaced with this statement. So the entire code will change in a simpler manner in this way. We can remove this entire thing and we can replace this with a simple one line statement while flag I equal true and turn equal to j. So this is nothing but the Peterson's algorithm, and there is no logical difference between the both algorithms. So simply we can say that the Peterson algorithm will also satisfy all the conditions of this solution, like it is a mutual exclusion, it guarantees progress, it guarantees bounded waiting. So therefore Peterson solution is also a perfect solution for synchronization. So in this way we have came to the end of a software solution with Peterson solution. In the next class we're going to discuss about the hardware solutions, and we'll see further using the semaphores and monitors in the upcoming classes. I hope you like this video. Thank you for watching.